Hello everyone, my name is Zahra Tabatabaei. I'm a SR9. I'm working in Tyris software company and I'm a Ph.D. student at UPV, University Polytechnic de Valencia.
Hello everyone, I'm Yuandou Wang from University of Amsterdam. I'm also working as a ESR2 in Collaborative project. I am studying virtual research environment in terms of decentralized workflow management. Our use cases include federated learning and privacy-preserving distributed machine learning.
Today we are going to talk about our recent paper, Worldwide Federated Content-Based Medical Image Retrieval. And now we are going to talk about what is content-based medical image retrieval. In a traditional content-based medical image retrieval, pathologists need to grab a tissue and analyze it to find the grade of that. And then sometimes they cannot make a decision about the grade. So they need to transfer it to other centers. Sometimes they need to send it to other countries, and they need to spend a lot of money for that. It takes a lot of time. So it's a lot of pressure for the patient. And meanwhile, the tissue would be loose. So this is time that we can use digital pathology. We can have a platform like content-based medical image retrieval. They can scan their images and they can share these scanned images together and analyze it and consult with other pathologists about the grade of that. So it can be quite faster for both society and of course for the pathologists. But of course, we're faced with some challenges in that. Lack of data, especially because they are medical data, it's difficult to share the data set. Low speed in training because they are really heavy and they are gigapixel images. So we need high performance GPU, and it's difficult to have that GPU in all centers and transferring data sets. So in our paper, we wanted to tackle this problem, and we reported our results into experiment, our potential way that we can tackle these problems and challenges thanks to federated learning. And these two experiments conduct with two different data sets, Common 17 and BRICHIS, that they are both breast cancer. And in the second experiment, we are using BRICHIS in 4 different magnification. And we assume 2 scenarios with that. First of all, we assume that there is no agreement for sharing images between centers. And second, we assume that there is an agreement just for sharing the retrieved images. So they can see the output, not the all images because of the storage problem. And there's an archive link for the paper for who is interested to see more details about the work. But to talk about it in deep, we can see the next slide.
Yeah, so okay, let's go for the first experiment in more details. As you can see in the picture, we implemented the centralized federated learning with a client-server architecture by using Flower framework, and we deployed our client programs onto 2 heterogeneous nodes located at the University of Amsterdam in the Netherlands and located in Tyris software in Spain, respectively. We also employed a cloud server funded by LifeWatch project to aggregate the distributed client training. We also tried different aggregation strategies, such as Fed-AVG and Fed-ADA grad strategies to train the different datasets, the Common 17 and the BRICHIS 46. As you can see in the upper, the Gantt chart shows the training time cost in our Fed-CBMR with the Fed-AVG aggregation strategy. And in a 2-round configuration, in total, the execution time in Fed-CBMR was around 6.15 hours to train 2 different datasets. However, in traditional CBMR, if we train the datasets twice, actually the total time could be 17 hours. So actually, by using federated learning work, actually in our Fed-CBMR, there was around 11 hours reduction.
So you can see the table and a video that is playing here. First, let's go for the table. We tried to tackle the needs for pathologists and AI experts. First, we need to have training our model in high accuracy and of course quite fast. So in comparison with Fed-CBIR with both aggregation method, we can see that we have higher accuracy in less training time in comparison with the traditional content-based medical image retrieval. But between Fed average and the other aggregation method, we conclude that Fed average can bring higher accuracy for us and also in less training time, almost 2 hours less than that. On the other hand, we can answer the question and the needs of pathologists because they need to have searching time really fast, so they can have they retrieve images quite fast, as you can see in the video. For example, if they have one query, they can retrieve 5 type similar patches in 0.29 seconds, so they can see the similar patterns in those retrieved images in 0.29 seconds. And also it has high accuracy for the retrieval, so they can have more accurate diagnosis.
In our second experience, actually, we extended 2 clients to 4 clients to train the breakest data sets with 4 different magnifications. We trained the data sets on 4 nodes located on 4 institutes from 3 cities across 2 countries by using Flower of New Work, of course.
In the second experiment, as I mentioned, we have 2 scenarios. In the first scenario, we said that there is no agreement between centers because of some security. They don't have any agreement and they can just share the weights together to train the more powerful model. So you can see that Fed CBIR is quite faster than traditional CBIR, and of course it brings higher accuracy for us. And for who is interested about confusion matrix, we put the confusion matrix of our paper in that it can show that the retrieved images could classify the work completely correct. And in the second experiment, we assume that in the second scenario, we assume that there's an agreement between centers that they can share retrieved images. What's the benefit of that? Whole slide images are some pathological data sets that they need a specific scanners. Having these scanners and in these equipment is really expensive. So some countries cannot have high performance scanners, so they cannot reach to high magnification, for example, 40, 200 or 100, and they can just provide 40x magnification for their images. So what they can do, for example, breast cancer that we were studying, the number of mitoses and measuring that is one of the important criteria for grading the breast cancer. And for that, they need to have higher magnification to see the pattern, to count the mitoses. So what can we do? The main goal of this scenario is that they have a query in 40x magnification and they upload it into their server, and they can retrieve images from all over the world with 40, 200, 400, or 100 magnification. This is something that we had for the breakest dataset because it has 4 magnification. So we mimic that position that they can retrieve images in 4 different magnification. So they can have just label, and also they can see the similar patterns, so they can have more accurate diagnosis.
We also had several lessons learned from Fed-CBMR, actually because of heterogeneity in federated learning ecosystem, such as the different data sets, heterogeneous infrastructures, and or even diverse users or models. Actually, they're still challenging because of heterogeneity, and it is still low efficiency in development and deployment, because it is still a lack of automation in the federated learning lifecycle pipeline, and lack of optimization in resource efficiency. So there are still improvements or still work to do for the time to increase the optimization. And one way we invested is to improve or optimize the federated learning deployment decisions.
And to have a quick conclusion, thanks to federated learning and Flower framework, we could improve the performance of traditional content-based medical image retrieval. So in that case, we could have higher accuracy in faster manner for training. And then we can have a more generalized model because we could retrieve images from other magnifications. And in that case, we need less power of GPU.
And in our future work, we hope we could expand global range beyond the policy borders with more countries around the world. We also are investing feed ops by automatically mapping the high-level workflow abstractions to distribute the resources, to optimize, to add more automation elements in federated learning operations. Thanks for your attention.
Thanks for the great talk.
Yeah, thank you for the talk. A great project, and it really a compliment on the project. It looks like a lot of work and such an important area to work on. I'm curious, what can we do from the Flower framework side to help you accelerate this?
So in terms of a framework, actually, I think by using a federated learning framework like Flower, actually it can speed up the development of centralized federated learning. Because in practice, conduct our experience by using Flower framework, it is not so time consuming to develop the federated learning code. Yeah, and the Flower framework helped us a lot to set up the federated learning setting.
Okay, great. Well, thank you so much again. Thank you for the talk.